In this video, we will go through the problems, the sample exercises in chapter 16. All of these problems are going to be about acids and bases, their relationships, how we can measure the strength of an acid, how we can measure the pH or pOH. Then we'll get into Ka, the acid dissociation constant, and Kb, which is the base dissociation constant. And then we'll talk a little bit about pKa and pKb. I'm going to start with sample exercise 16.1, which asks us for the conjugate base. I'm going to abbreviate that CB here. And it gives us 4 different substances that we need to get the conjugate base for. So we have HClO4, H2S, pH4 positive, HCO3 minus. And this asks us to find the conjugate base of each one of these acids. In order to do that, all we have to do is remove a proton. And remember, a proton is H plus. So we'll just remove a proton from each one of these. If we take away this proton here, then that's going to leave us with ClO4, and then we'll have a minus charge on that because we're taking the H, but that is positive, which means that this, which was overall did not have a charge, is now going to have a -1. H2S has 2 hydrogens. We will take one of those away, and again, that's going to leave us with a negative charge there. For this one, the pH4 plus, we have a plus there already, so when we take away a hydrogen, we'll have 3 left. That plus sign is going to go with it. So we're just left with pH3. And then finally, when we take the H here, we're going to have CO3. We already had -1. We're taking away, that positive H plus. That's going to leave us with 2 minus now. The second part of this asks us to find the conjugate acid of several bases. So let me write those. So if to find the conjugate base, we remove a proton, then to find the conjugate acid, we are going to add a proton. So I'm just going to go through here and add an H plus to each one of these. So when I do that, we'll have HCN because that plus and minus, we know that that evens out. So we're going to have a neutral compound here. When I add an H here, that's going to reduce the 2 minus just to minus. H2O, we know, becomes a hydronium ion when we add a hydrogen to it. And then for HCO3, when I add another hydrogen, that becomes H2, CO3, and that eliminates the negative charge out there. So that is sample exercise 16.1. Sample exercise 16.2 wants us to write an equation. We're given the hydrogen sulfite ion, which is HSO3 minus. And so they're going to ask us here to write an equation for the reaction of HSO3 with water. in which the ion acts as an acid, and then in which the ion acts as a base. So this hydrogen sulfide ion is an example of an amphiprotic substance where it can act as an acid and a base. Kind of like we saw up here with the HCO3 minus, it could act as an acid and a base. So they want us to combine this with water. So that's going to be in an aqueous solution. I'm going to add that to water, which would be liquid. And I know my reaction is going to be reversible. So in this first one, we want it to act like an acid. And that means that it's going to donate a proton. So it's going to donate the hydrogen ion. So if we get rid of the hydrogen ion here, then that's going to leave us with SO3. It was already 1 minus, so now it's going to become a 2 minus charge. That proton has to go somewhere. It's going to attach to the water molecule here. And so that's going to become the hydronium ion. Ran out of room there. So we'll have the hydronium ion. So then it wants us to do the same thing in B, in that we're going to combine it with water, but this time we want it to act like a base. So it will accept a proton. So it's going to accept that hydrogen ion. So this time we're going to add another hydrogen here. So we're going to have H2SO3, and we're going to not have any charge because the plus and the minus, we know that's a neutral overall charge. Okay. And it's taking, this time it accepts the hydrogen. Where is it getting the hydrogen? It's getting the hydrogen from water. So what's left is 1 hydrogen and 1 oxygen. That is our hydroxide ion, and that's what's going to be left. So if we look at these in acid conjugate base, base conjugate acid pairs, this would be our acid because we wanted it to act like an acid. So then this would have to be our base. So the SO3 2 minus here would be our conjugate base, and the hydronium would be the conjugate acid. In our second example here, it acts like the base. So then water in this case acts like an acid. So the H2SO3 would be our conjugate acid, and the OH, the hydroxide ion, would be the conjugate base. So let's move on now to sample exercise 16.3. We are provided with a reaction, and it tells us to use figure 16.4 to predict whether the equilibrium lies to the left or to the right. So we're given this equation. And they want to know, where is the equilibrium? Does it lie to the left or does it lie to the right? So the way that we have to do this is they told us to use figure 16.4, and that's going to allow us to determine the strength of our acids and bases. Figure 16.4 is found on page 676 in your book, and I also put it in the notes handout for you. What this does is it gives us the strengths of our conjugate acid-base pairs. So this is what we're going to be using for this question, all right? And we're going to find the acid that we're using here, which is HSO4. We see its conjugate base over here that is in our equation. And then we also look for our base, which is CO3 2 minus. We find it down here and the conjugate acid across from it. So what you see on this diagram is that these acids here are the strongest. And then on the base side, the bases down here are the strongest. So what we have to do in looking at figure 16.4 in determining the strength of our acids and bases is figure out, is HSO4 minus a stronger acid than CO3 2 minus a base? And when we see where those lie, where I showed you, we see that HSO4 minus is a stronger acid than CO3 2 minus is a base. So HSO4 minus is a stronger acid than the CO3 2 minus is a base. And we see that the CO3 2 minus is a stronger base than the conjugate base of SO4. So therefore, both of these are our reactants, and equilibrium is favoring these reactants in that the hydrogen here is transferred from the HSO4 to the CO3, and that because these are stronger, I think I misspoke here for a second, because this is a stronger acid and this is a stronger base, we have to produce more product. So since our stronger ones are on the reactant side, then equilibrium is going to favor the production of the products. These are going to separate, and this hydrogen, or the hydrogen is going to separate from this, join its conjugate base over here, and so we're going to have a situation where these two are the strongest. The strongest are on the product side or the reactant side, so that means we're going to produce more product. So equilibrium then is going to lie to the right, okay, because it favors the product. Now, in that same exercise, practice exercise, where's that? Practice exercise 2A gives us another example. So we have HPO4, 2 minus, plus water, gives us H2PO4 minus, plus OH. Now, when I use figure 16.4, what I find out is that this time my H2PO4 is a stronger acid than the HPO4 2 minus, okay? And OH is a stronger base, so a stronger acid, stronger base, than water. So now my products are stronger. So since my products are stronger, we have to produce more reactant. So in this example, the equilibrium lies to the left. So how do you work these? Well, you look at each substance. You find the side that has the stronger acid and base, and that tells you that the reaction then will proceed away from that because we're going to produce more, in this case, reactant, in this case, more product. And so equilibrium, if the reactants are stronger, then equilibrium is going to lie to the right on the product side. If the products are stronger, then we're going to produce more products. So equilibrium lies to the left. All right, so that is 16.3. The next section gets into the auto-ionization of water, and we have a new expression for this called the ion product constant of water, and that is what's going to allow us then to determine our hydrogen, our proton, and our hydroxide ion concentrations that then are going to let us determine pH. So we're going to skip to sample exercise 16.5, and it asks us to calculate concentration of hydrogen ions in a couple of different circumstances here. So in 16.5, we're asked to find the hydrogen ion concentration in two different solutions. One in which our hydroxide concentration is 0.010 molar, and then in another when that hydroxide ion concentration is 1.8 times 10 to the negative 9. And we're trying to figure out, okay, what is our hydrogen ion concentration? Well, we're going to use the auto-ionization reaction for water and look at our expression for that ion constant for water and use it to solve these problems. So hydrogen ion concentration times hydroxide ion concentration equals 1.0 times 10 to the negative 14. This holds true as long as the temperature is 25 degrees Celsius, or right around 25 degrees Celsius. And they tell us in this problem and all the problems that follow, we assume, unless stated otherwise, that the temperature is 25 degrees Celsius. So I don't have to worry about temperature here because they've told me that it's 25 degrees Celsius. So now all I have to do is plug in the hydroxide values that I've been given and solve for hydrogen ion concentration. So in the first one here, I've got hydrogen ion concentration times hydroxide 0.010, and that's going to be equal to the 1 times 10 to the negative 14. So I divide both sides by 0.010 molar or 0.010 molar. And for this first one, I end up with 1.0 times 10 to the negative 12. And for the second one, I'm going to do the same thing, kind of squeeze that in here. And that one comes out to be 5.6 times 10 to the negative 6 molar. So that's all we have to do if we are given hydrogen ion concentration or hydroxide ion concentration and asked to find the other, then we just use this equation right here to do that. Sample exercise 16.6 asks us to determine a pH for the samples that we have recorded or that we calculated in 16.5. So pH is equal to the negative log of the hydrogen ion concentration. So when I look back to what those hydrogen ion concentrations were that I calculated, one of those, part A, was 1.0 times 10 to the negative 12, and then B was 5.6 times 10 to the negative 6. So all I have to do in exercise 16.6 is just plug that in. So A, we're going to say pH is equal to the negative log, and I'll plug that in, 1.0 times 10 to the negative 12. And when I plug that into my calculator, I get the log of 12 is, or the log of 1.0 times 10 to the negative 12 is negative 12. So I've got negative 12, so my pH is 12. So you can see from this example that if your number here is 1.0, then you can just look at the exponent up here and take the negative of that. So negative of a negative 12 is going to be a positive 12. So the pH is 12. Now in B, we can't do that because we don't have the 1.0 there. It is 5.6 times 10 to the negative 6. So when I plug that into the calculator, I get 5.25 as my pH. So just remember the formula for pH is negative log H. Now, how you put this in your calculator may be a little different. I know for Apple calculator, like if you're using your iPhone, you probably will have to put in the hydrogen ion concentration first and then hit log and hit enter and then take the negative of that. But just make sure that you are clear on how you put this into your calculator. Moving on to exercise 16.7. A sample of freshly pressed apple juice has a pOH of 10.24. What is the hydrogen ion concentration? So we're going to have to use another formula here. First things first, we need to get to our pH. So we're given pOH, we need pH. We say 14 minus our pOH is going to give us pH. So that's going to be 14 minus 10.24. So our pH is 3.76. And we're asked to find the hydrogen ion concentration. So we know that from our previous example, pH is equal to the negative log of the hydrogen ion concentration. So 3.76 is equal to negative log of H. Well, we have to do what is called the anti-log in order to solve this problem. So if you know your pH and you're asked to find the hydrogen ion concentration, you're going to take 10 and you're going to raise it to the power of the negative pH. So 10 to the power of negative pH. All right. So we're going to have 10 raised to negative 3.76. And when we put that in our calculator, 10, and then you'll probably have to use either the XY button or you may have a caret button that you'll use, and you'll put in this exponent here. Our hydrogen ion concentration then is going to equal 1.7 times 10 to the negative 4. And of course, that'll be molar here. Now, you'll notice something, or you may have noticed something as we've been going through this, that pH is going to be given with 2 decimals. So anytime you calculate a pH, make sure you go to 2 decimal places. Okay. Now, moving on to 16.8, what is the pH of a 0.040 molar solution of HClO4? Now, when you are asked to calculate pH of a particular molar solution, and we're going to look at 2 of these, 16.8 and 16.9, the first thing we have to do is determine, is this one of our strong acids or strong bases? Now, on page 684 in your book and also in your notes, you have a list of what we refer to as strong acids: HCl, HBr, HI, HNO3, HClO3, HClO4, and H2SO4. Now, these are called strong acids because they are strong electrolytes. They will completely dissociate when you put them in water. Now, what does that mean? Well, it's going to completely dissociate into hydrogen ions and perchlorate ions, so that this molar solution basically becomes the molar solution of the hydrogen ions that are going to be found there. So when you're asked to find the pH of one of these strong acids, then you know that it completely dissociates. So the molarity concentration, or the molar concentration of hydrogen ions, is equal to the molar concentration of the acid. So we just plug it into our formula. pH equals negative log of 0.40. And when we calculate that, it ends up to be 1.40. So you can't just automatically assume that your molar concentration of your acid or your base is going to equal the molar concentration here of the products. You have to determine first, is it a strong acid? Is it a strong base? So refer to your list. Yes, perchloric acid is a strong acid, so it's going to completely dissociate. So my pH is going to be equal to the negative log of the molar concentration of the acid. So I get 1.40. Now let's look at 16.9. So 16.9 asks us kind of the same question. The pH of 2 different bases here. We have sodium hydroxide and calcium hydroxide, and we're asked to determine the pH. So when we look at the pH for these 2, are they strong bases? Well, on page 685, you have a list of strong bases. They are the ionic hydroxide of your alkali metals. So that's going to be your group 1. So sodium, potassium, continuing from there. And the ionic hydroxide of the heavier alkaline earth metals, which are in the second group, such as strontium hydroxide. So we know that sodium hydroxide is a strong base. So kind of like our perchloric acid here, when it dissociates, so when we put it into water, it will completely dissociate into its individual ions. Okay, so then the concentration of the hydroxide ions is equal to the concentration of the molarity of the solution. So the OH the hydroxide concentration is going to equal this. All right. So there are a couple of different ways that you can figure this out. You can use the ion constant of water and plug in the molar concentration of the hydroxide and solve for the hydrogen ion concentration like we did back over here in 16.5, and then take the pH like we did in 16.6. Or you can determine the pOH and from there determine pH. So pOH is just like pH, except we're going to take the negative log of the hydroxide ion concentration. Okay, so they're exactly the same, except pH is the negative log of hydrogen ion, pOH negative log of the hydroxide ion. Okay, so let's work it out this way. So the negative log, we know it's equal to our molar concentration of our substance, so we're going to plug that in there. And so our pOH is going to give us 1.55. Then we use our formula from right here, where pH and pOH add up to be 14. So then my pH will equal 14 minus my pOH, which is 1.55. So my pH is 12.45. Okay. So what I did is I found my pOH by taking the negative log of the hydroxide ion concentration. And once I got that, I subtracted it from 14 to get my pH. So here's my pH for A. Okay, so this is A. Now, B, we have a different solution. We have calcium hydroxide. So it is a strong base. It's one of the heavier alkaline earth metals. So it will also completely dissociate in water. But here's where we differ. Notice with sodium hydroxide, I have one sodium and one hydroxide. But over here with calcium, I have one calcium and two hydroxides. Okay, so when this one dissociates, okay, it's going to be a little different. So let's look at what happens here. When this one dissociates, right, I have 2 moles of hydroxide ions. So for every 1 calcium, I have 2 hydroxides, right? Because it takes 2 hydroxides to make a neutral molecule or neutral compound with calcium. So I have to do this a little bit different. My molar concentration of the calcium hydroxide was 0.0011. But I have 2 times that now. Since I have 2 hydroxides, I have to multiply this initial concentration times 2 so that I have 0.0022 moles of hydroxide. So now I can plug it in to my formula, negative log, and I'm going to use 0.0022 because I have 2 moles. So I have to multiply that molar concentration times 2. That gives me 2.66. So then I subtract. pH is equal to 14 minus 2.66, and that gives me 11.34. So when working out these pH problems like this, you have to decide, is it a strong acid or a strong base? If yes, and you have a 1-to-1 molar ratio like we did here and here, then you just take the negative log of that molar concentration. That gives you your pOH. Subtract that from 14 to get your pH. If you have more than 1 mole of hydroxide, then you're going to have to multiply your molar concentration of the starting solution times how many ever moles of hydroxide you have. Usually it's going to be 2. And then take the negative log of that and subtract from 15. The second part of this chapter gets into a little bit more math. Now we're going to actually get into the acid dissociation constant and base dissociation constant. We have to use those when we're not dealing with a strong acid or base. So if we have a weak acid or base that doesn't completely ionize in water, we have to use a different formula or a different series of formulas to get the solution. So I'll record an additional video going through the more difficult concentrations concerning